Welcome back to this course, Fundamentals of Computer Architecture. This lesson summarizes the pipelining module. We are now at the end of the review of pipelining. A brief summary. We can increase the CPU clock frequency and hence the performance of applications by pipelining instructions. The canonical MIPS pipeline consists of 5 stages: instruction fetch, instruction decode, execute, memory access, and write back. In the IF stage, the instruction is fetched and the PC is incremented. In the ID stage, the instruction is decoded and the register file is read, which is assumed to take place in the second half of the clock cycle. In the execute stage, the instruction is executed, or the effective memory address is calculated if the instruction is a load or stored, or the branch condition and target address are calculated. In the mem stage, loads and stores access memory. All other instructions bypass the memory as indicated by the bypass path in this pipeline diagram. Finally, in the write back stage, all instructions that produce a result that write a register write back this result to the register file, which is assumed to occur in the first half of the clock cycle as indicated by the blue color on the left of the register file in this pipeline diagram. I always joke to my students, the MIPS designers had 3 things in mind when they designed the MIPS instruction set: pipelining, pipelining, and pipelining. This might be a little joke, but the MIPS ISA really was designed with pipelining in mind. In particular, all instructions are 4 byte, which allows to increase the PC already in the instruction fetch stage. The source registers are always in the same place in the instruction format, which allows to read the register file before the instruction has been decoded. And third, MIPS is a load-store architecture, meaning that only loads and stores access memory, which also simplifies pipelining. Finally, in this summary, there are pipelining problems known as hazards and about possible solutions to these hazards. Structural hazards happen if the hardware doesn't allow the execution of the next instruction in the next clock cycle, and they can be solved by replicating functional units or enhancing their capabilities. Data hazards occur when there is a dependency with an instruction still in the pipeline, and they can, at least in most cases, be solved by forwarding. In case of a load use hazard, however, forwarding cannot prevent a stall cycle. Compilers try to avoid such stalls by reordering instructions. Finally, control hazards occur because at the time branches are executed, some other instructions already entered the pipeline. They can be solved partially by executing branches early in the pipeline, and we showed how branch execution could be moved to the second stage of the canonical pipeline, the ID stage. At that time, the next instruction has already been fetched, but this instruction does not need to be flushed if we employ branch delay slot. We also saw that the branch delay slot can be filled with an instruction from before the branch, from the branch target, and from the fall-through path. Finally, another way of dealing with branch hazards is branch prediction, which we will study in more detail in a lesson to come. I still owe you the answer to the question, why do all MIPS processors implement the branch delay slot, even though their performance would be just as good or perhaps even better without the branch delay slot? The answer is binary compatibility. To provide binary code compatibility. In order to correctly execute MIPS code, it is necessary that the instructions after all branches be executed. This was the case on the first MIPS processor, and to ensure that code that ran correctly on that processor runs correctly on all MIPS processors implement the branch delayed step.
This completes this lesson. Thanks for watching. In the next lesson, I will present an exercise that shows how code will be executed on the canonical 5-stage pipeline when forwarding occurs and when a stall is needed. Hope to see you back.